Data is the foundation of modern artificial intelligence. Every learning system depends on data to form patterns, make predictions, and generate outputs. Without data, AI systems cannot adapt or improve, regardless of how advanced their algorithms or architectures may be. An AI system without data cannot learn. Rules alone are insufficient for handling complexity and variation in the real world. Data provides the examples from which systems infer relationships and generalize behavior. In AI, data refers to structured representations of observations about the world. These representations can take many forms, but they always serve as inputs that models use to learn statistical patterns. Data is not the same as knowledge. Data consists of raw observations, while knowledge emerges when models learn regularities and relationships within that data through training. Real-world phenomena must be measured and digitized before they become usable as data. This process involves sensors, recording systems, and human decisions about what to capture and how. Data is always a proxy for reality, not reality itself. It captures partial, simplified views of complex systems, and inevitably omits context, nuance, and unmeasured factors. AI systems rely on many types of data. Broadly, data can be classified as structured or unstructured, depending on how formally it is organized. Structured data follows fixed schemas, such as tables with rows and columns. It is common in databases and spreadsheets, and is relatively easy for algorithms to process. Unstructured data lacks a predefined format. Text, images, audio, and video fall into this category and require more complex processing techniques. Some data is semi-structured, combining elements of both forms. Logs and metadata often follow patterns but allow flexibility, requiring additional interpretation. Numerical data represents quantities such as measurements, counts, or continuous values. Many AI models rely heavily on numerical representations during computation. Categorical data represents discrete classes or labels. Examples include categories, types, or identifiers that group observations into defined sets. Text data represents language as sequences of symbols or tokens. AI systems process these sequences statistically rather than understanding meaning. Image data consists of pixels arranged spatially. Models learn patterns such as edges, shapes, and textures from these pixel values. Audio data represents sound as waveforms over time. AI systems extract temporal patterns to recognize speech, music, or other acoustic signals. Video data combines spatial and temporal information. Models must process both visual structure and motion, increasing complexity significantly. Dataset size influences learning. Larger datasets often enable better generalization, but only when the data is relevant and representative. Variety matters as much as volume. Diverse data helps models handle a wider range of situations and reduces overfitting to narrow conditions. Some systems rely on static datasets, while others process streaming data. Real-time data introduces additional challenges such as latency and drift. Data quality directly affects model performance. Errors, inconsistencies, and missing values can degrade learning and reliability. Noisy data contains mistakes or irrelevant information. Cleaning data is often necessary but rarely perfect, requiring trade-offs. Bias arises when data is unbalanced or unrepresentative. Models trained on biased data will reflect and potentially amplify those biases. Data is never neutral. Decisions about what to collect, label, and include reflect human values, priorities, and constraints. Sampling determines which cases appear in a dataset. Exclusions can be as influential as inclusions, shaping what models learn. Labels provide meaning to data, but they are created by humans. This introduces subjectivity, disagreement, and contextual interpretation. Ground truth is often uncertain. Even experts may disagree, and some concepts lack clear or objective definitions. The phrase, garbage in, garbage out, captures a central principle. Poor quality data leads to poor quality outputs, regardless of model sophistication. More data does not always mean better data. Large data sets can reinforce biases or redundancies if not carefully curated. Data leakage occurs when information unintentionally enters training or evaluation. This can create misleading performance results. Training data often differs from real-world data. When distributions shift, models may perform poorly outside controlled conditions. Data drift occurs when patterns change over time. Systems must be monitored and updated to remain effective. Collecting data requires resources. Time, labor, and financial cost often exceed the cost of model development itself. Data must be maintained. Outdated or irrelevant data can harm system performance if not refreshed. Questions of ownership affect who can use data and how. Legal and contractual constraints shape AI development. Privacy concerns arise when data involves individuals. Protecting personal information is both an ethical and regulatory requirement. Data governance establishes rules for collection, storage, access, and use. Strong governance supports accountability and trust. Documentation provides context about data sources, limitations, and intended use. Without it, data can be misapplied. Preparation and pre-processing strongly influence outcomes. Many performance gains come from better data handling rather than better models. Humans play a central role in data work. Curation, labeling, and review require judgment that cannot be fully automated. Automation alone cannot resolve ambiguity. Human oversight remains essential for interpreting context and resolving edge cases. Data increasingly functions as infrastructure. It is a long-term asset that supports multiple systems over time. Organizations with access to high-quality data gain competitive advantages. Data availability shapes who can build effective AI systems. Open data promotes accessibility and research, while closed data protects proprietary value. Each approach involves trade-offs. Ethical data use requires consent, fairness, and respect for affected individuals. These considerations shape responsible AI practices. Data shapes model behavior. The patterns learned during training determine how systems respond in deployment. Models reflect the data they are trained on. Assumptions and limitations embedded in data become embedded in outputs. In many projects, data is the true bottleneck. Algorithms and compute are often secondary constraints. Working with data is difficult because reality is messy. Continuous effort is required to manage change and complexity. The central takeaway is clear. Data defines both the power and the limits of artificial intelligence systems. Next, we will examine features and how AI systems transform raw data into representations that models can use to make predictions.